NCERT Class 11th. Chapter Reading. Unit 1. Some Basic Concepts of Chemistry. Objective. After studying this unit, you will be able to appreciate the contribution of India in the development of chemistry, understand the role of chemistry in different spheres of life, explain the characteristics of three states of matter, classify different substances into elements, compounds and mixtures, use scientific notations and determine significant figures, differentiate between precision and accuracy, define SI base units and convert physical quantities from one system of units to another, explain various laws of chemical combination, appreciate significance of atomic mass, average atomic mass, molecular mass and formula mass, describe the terms, mole and molar mass, calculate the mass % of component elements constituting a compound, determine empirical formula and molecular formula for a compound from the given experimental data, and perform the stoichiometric calculations. Chemistry is the science of molecules and their transformations. It is the science not so much of the 100 elements but of the infinite variety of molecules that may be built from them. Science can be viewed as a continuing human effort to systematize knowledge for describing and understanding nature. You have learnt in your previous classes that we come across diverse substances present in nature and changes in them in daily life. Curd formation from milk, formation of vinegar from sugarcane juice on keeping for prolonged time, and rusting of iron are some of the examples of changes which we come across many times. For the sake of convenience, science is subdivided into various disciplines: chemistry, physics, biology, geology, etc. The branch of science that studies the preparation, properties, structure and reactions of material substances is called chemistry. Development of chemistry. Chemistry, as we understand it today, is not a very old discipline. Chemistry was not studied for its own sake, rather it came up as a result of search for two interesting things: 1. Philosopher's stone, Paris, which would convert all baser metals, example, iron and copper, into gold; 2. Elixir of life, which would grant immortality. People in ancient India already had the knowledge of many scientific phenomena much before the advent of modern science. They applied that knowledge in various walks of life. Chemistry developed mainly in the form of alchemy and iatrochemistry during 1300 to 1600 Common Era. Modern chemistry took shape in the 18th century Europe, after a few centuries of alchemical traditions which were introduced in Europe by the Arabs. Other cultures, especially the Chinese and the Indian, had their own alchemical traditions. These included much knowledge of chemical processes and techniques. In ancient India, chemistry was called Rasayan Shastra, Rastantra, Raskriya or Rasvidya. It included metallurgy, medicine, manufacture of cosmetics, glass, dyes, etc. Systematic excavations at Mohenjo-daro in Sindh and Harappa in Punjab prove that the story of development of chemistry in India is very old. Archaeological findings show that baked bricks were used in construction work. It shows the mass production of pottery, which can be regarded as the earliest chemical process, in which materials were mixed, molded and subjected to heat by using fire to achieve desirable qualities. Remains of glazed pottery have been found in Mohenjo-daro. Gypsum cement has been used in the construction work. It contains lime, sand and traces of calcium carbonate. Harappans made faience, a sort of glass which was used in ornaments. They melted and forged a variety of objects from metals, such as lead, silver, gold and copper. They improved the hardness of copper for making artifacts by using tin and arsenic. A number of glass objects were found in Maski in South India, 1000 to 900 BCE, and Hastinapur and Taxila in North India, 1000 to 200 BCE. Glass and glazes were colored by addition of coloring agents like metal oxides. Copper metallurgy in India dates back to the beginning of Chalcolithic cultures in the subcontinent. There are much archaeological evidences to support the view that technologies for extraction of copper and iron were developed indigenously. According to Rigveda, tanning of leather and dyeing of cotton were practiced during 1000 to 400 BCE. The golden gloss of the black polished ware of northern India could not be replicated and is still a chemical mystery. These wares indicate the mastery with which kiln temperatures could be controlled. Kautilya's Arthashastra describes the production of salt from sea. A vast number of statements and material described in the ancient Vedic literature can be shown to agree with modern scientific findings. Copper utensils, iron, gold, silver ornaments and terracotta discs and painted grey pottery have been found in many archaeological sites in North India. Sushruta Sanhita explains the importance of alkalis. The Charaka Sanhita mentions ancient Indians who knew how to prepare sulfuric acid, nitric acid and oxides of copper, tin and zinc, the sulfates of copper, zinc and iron and the carbonates of lead and iron. Rasopanishada describes the preparation of gunpowder mixture. Tamil texts also describe the preparation of fireworks using sulfur, charcoal, saltpeter, that is, potassium nitrate, mercury, camphor, etc. Nagarjuna was a great Indian scientist. He was a reputed chemist, an alchemist and a metallurgist. His work Rasratnakar deals with the formulation of mercury compounds. He has also discussed methods for the extraction of metals, like gold, silver, tin and copper. A book, R. Sarnavam, appeared around 800 Common Era. It discusses the uses of various furnaces, ovens and crucibles for different purposes. It describes methods by which metals could be identified by flame color. Chakrapani discovered mercury sulfide. The credit for inventing soap also goes to him. He used mustard oil and some alkalis as ingredients for making soap. Indians began making soaps in the 18th century Common Era. Oil of erinda and seeds of maua plant and calcium carbonate were used for making soap. The paintings found on the walls of Ajanta and Ellora, which look fresh even after ages, testify to a high level of science achieved in ancient India. Varamihir's Brihat Sanhita is a sort of encyclopedia, which was composed in the 6th century Common Era. It informs about the preparation of glutinous material to be applied on walls and roofs of houses and temples. It was prepared entirely from extracts of various plants, fruits, seeds and barks, which were concentrated by boiling, and then treated with various resins. It will be interesting to test such materials scientifically and assess them for use. A number of classical texts, like Atharvaveda, 1000 BCE, mention some dye stuff. The material used were turmeric, madder, sunflower, opiment, cochineal and lac. Some other substances having tinting property were Campylsiaca, Patanga and Jatuka. Varamihir's Brihat Sanhita gives references to perfumes and cosmetics. Recipes for hair dyeing were made from plants, like indigo and minerals like iron power, black iron or steel and acidic extracts of sour rice gruel. Gandhayukli describes recipes for making scents, mouth perfumes, bath powders, incense and talcum powder. Paper was known to India in the 17th century as account of Chinese traveler Ayazing describes. Excavations at Taxila indicate that ink was used in India from the 4th century. Colors of ink were made from chalk, red lead and minimum. It seems that the process of fermentation was well known to Indians. Vedas and Kautilya's Arthashastra mention about many types of liquors. Charaka Sanhita also mentions ingredients, such as barks of plants, stem, flowers, leaves, woods, cereals, fruits and sugarcane for making asavas. The concept that matter is ultimately made of indivisible building blocks appeared in India a few centuries BCE as a part of philosophical speculations. Acharya Kanda, born in 600 BCE, originally known by the name Kashyap, was the first proponent of the atomic theory. He formulated the theory of very small indivisible particles, which he named Paramanu, comparable to atoms. He authored the text Vaisheshika Sutras. According to him, all substances are aggregated form of smaller units called atoms, Paramanu, which are eternal, indestructible, spherical, suprasensible and in motion in the original state. He explained that this individual entity cannot be sensed through any human organ. Kanda added that there are varieties of atoms that are as different as the different classes of substances. He said these paramanu could form pairs or triplets. Among other combinations, and unseen forces cause interaction between them. He conceptualized this theory around 2,500 years before John Dalton, 1766 to 1844. Charaka Sanhita is the oldest Ayurvedic epic of India. It describes the treatment of diseases. The concept of reduction of particle size of metals is clearly discussed in Charaka Sanhita. Extreme reduction of particle size is termed as nanotechnology. Charaka Sanhita describes the use of bhasma of metals in the treatment of ailments. Nowadays, it has been proved that bhasmas have nanoparticles of metals. After the decline of alchemy, iatrochemistry reached a steady state. But it too declined due to the introduction and practice of Western medicinal system in the 20th century. During this period of stagnation, pharmaceutical industry based on Ayurveda continued to exist, but it too declined gradually. It took about 100 to 150 years for Indians to learn and adopt new techniques. During this time, foreign products poured in. As a result, indigenous traditional techniques gradually declined. Modern science appeared in Indian scene in the later part of the 19th century. By the mid-19th century, European scientists started coming to India and modern chemistry started growing. From the above discussion, you have learned that chemistry deals with the composition, structure, properties and interaction of matter and is of much use to human beings in daily life. These aspects can be best described and understood in terms of basic constituents of matter that are atoms and molecules. That is why chemistry is also called the science of atoms and molecules. Can we see, weigh and perceive these entities, atoms and molecules? Is it possible to count the number of atoms and molecules in a given mass of matter and have a quantitative relationship between the mass and the number of these particles? We will get the answer of some of these questions in this unit. We will further describe how physical properties of matter can be quantitatively described using numerical values with suitable units.
1.1 Importance of chemistry. Chemistry plays a central role in science and is often intertwined with other branches of science. Principles of chemistry are applicable in diverse areas,
such as weather patterns, functioning of brain and operation of a computer, production in chemical industries, manufacturing fertilizers, alkalis, acids, salts, dyes, polymers, drugs, soaps, detergents, metals, alloys, etc., including new material. Chemistry contributes in a big way to the national economy. It also plays an important role in meeting human needs for food, healthcare products and other material aimed at improving the quality of life. This is exemplified by the large-scale production of a variety of fertilizers, improved variety of pesticide and insecticides. Chemistry provides methods for the isolation of life, saving drugs from natural sources and makes possible synthesis of such drugs. Some of these drugs are cisplatin and Taxol, which are effective in cancer therapy. The drug AZT, azithromycin, is used for helping AIDS patients. Chemistry contributes to a large extent in the development and growth of a nation. With a better understanding of chemical principles, it has now become possible to design and synthesize new material having specific magnetic, electric and optical properties. This has led to the production of superconducting ceramics, conducting polymers, optical fibers, etc. Chemistry has helped in establishing industries which manufacture utility goods, like acids, alkalis, dyes, polymers, metals, etc. These industries contribute in a big way to the economy of a nation and generate employment. In recent years, chemistry has helped in dealing with some of the pressing aspects of environmental degradation with a fair degree of success. Safer alternatives to environmentally hazardous refrigerants, like CFCs, chlorofluorocarbons, responsible for ozone depletion in the stratosphere, have been successfully synthesized. However, many big environmental problems continue to be matters of grave concern to the chemists. One such problem is the management of the greenhouse gases, like methane, carbon dioxide, etc. Understanding of biochemical processes, use of enzymes for large-scale production of chemicals and synthesis of new exotic material are some of the intellectual challenges for the future generation of chemists. A developing country, like India, needs talented and creative chemists for accepting such challenges. To be a good chemist and to accept such challenges, one needs to understand the basic concepts of chemistry, which begin with the concept of matter. Let us start with the nature of matter. 1.2. Nature of matter. You are already familiar with the term matter from your earlier classes. Anything which has mass and occupies space is called matter. Everything around us, for example, book, pen, pencil, water, air, all living beings, etc., are composed of matter. You know that they have mass and they occupy space. Let us recall the characteristics of the states of matter, which you learnt in your previous classes. 1.2.1. States of matter. You are aware that matter can exist in three physical states, viz. solid, liquid and gas. The constituent particles of matter in these three states can be represented as shown in Fig. 1.1. Particles are held very close to each other in solids in an orderly fashion and there is not much freedom of movement. In liquids, the particles are close to each other but they can move around. However, in gases, the particles are far apart as compared to those present in solid or liquid states and their movement is easy and fast. Because of such arrangement of particles, different states of matter exhibit the following characteristics. 1. Solids have definite volume and definite shape. 2. Liquids have definite volume but do not have definite shape. They take the shape of the container in which they are placed. 3. Gases have neither definite volume nor definite shape. They completely occupy the space in the container in which they are placed. These three states of matter are interconvertible by changing the conditions of temperature and pressure. Solid, liquid, gas. On heating, a solid usually changes to a liquid, and the liquid on further heating changes to gas or vapor. In the reverse process, a gas on cooling liquefies to the liquid and the liquid on further cooling freezes to the solid. 1.2.2 Classification of matter. In Class 9, Chapter 2, you have learned that at the macroscopic or bulk level, matter can be classified as mixture or pure substance. These can be further subdivided as shown in Figure 1.2. When all constituent particles of a substance are same in chemical nature, it is said to be a pure substance. A mixture contains many types of particles. A mixture contains particles of two or more pure substances which may be present in it in any ratio. Hence, their composition is variable. Pure substances forming mixture are called its components. Many of the substances present around you are mixtures. For example, sugar solution in water, air, tea, etc. are all mixtures. A mixture may be homogeneous or heterogeneous. In a homogeneous mixture, the components completely mix with each other. This means particles of components of the mixture are uniformly distributed throughout the bulk of the mixture and its composition is uniform throughout. Sugar solution and air are the examples of homogeneous mixtures. In contrast to this, in a heterogeneous mixture, the composition is not uniform throughout and sometimes different components are visible. For example, mixtures of salt and sugar, grains and pulses along with some dirt, often stone pieces, are heterogeneous mixtures. You can think of many more examples of mixtures which you come across in the daily life. It is worthwhile to mention here that the components of a mixture can be separated by using physical methods, such as simple hand-picking, filtration, crystallization, distillation, etc. Pure substances have characteristics different from mixtures. Constituent particles of pure substances have fixed composition. Copper, silver, gold. Water and glucose are some examples of pure substances. Glucose contains carbon, hydrogen and oxygen in a fixed ratio and its particles are of same composition. Hence, like all other pure substances, glucose has a fixed composition. Also, its constituents, carbon, hydrogen and oxygen, cannot be separated by simple physical methods. Pure substances can further be classified into elements and compounds. Particles of an element consist of only one type of atoms. These particles may exist as atoms or molecules. You may be familiar with atoms and molecules from the previous classes, however, you will be studying about them in detail in Unit 2. Sodium, copper, silver, hydrogen, oxygen, etc. are some examples of elements. They're all atoms are of one type. However, the atoms of different elements are different in nature. Some elements, such as sodium or copper, contain atoms as their constituent particles, whereas, in some others, the constituent particles are molecules which are formed by two or more atoms. For example, hydrogen, nitrogen and oxygen gases consist of molecules, in which two atoms combine to give their respective molecules. This is illustrated in Figure 1.3. When two or more atoms of different elements combine together in a definite ratio, the molecule of a compound is obtained. Moreover, The constituents of a compound cannot be separated into simpler substances by physical methods. They can be separated by chemical methods. Examples of some compounds are water, ammonia, carbon dioxide, sugar, etc. The molecules of water and carbon dioxide are represented in Figure 1.4. Note that a water molecule comprises 2 hydrogen atoms and 1 oxygen atom. Similarly, a molecule of carbon dioxide contains 2 oxygen atoms combined with 1 carbon atom. Thus, the atoms of different elements are present in a compound in a fixed and definite ratio, and this ratio is characteristic of a particular compound. Also, the properties of a compound are different from those of its constituent elements. For example, hydrogen and oxygen are gases, whereas the compound formed by their combination, that is, water, is a liquid. It is interesting to note that hydrogen burns with a pop sound and oxygen is a supporter of combustion, but water is used as a fire extinguisher. 1.3. Properties of matter and their measurement. 1.3.1. Physical and chemical properties. Every substance has unique or characteristic properties. These properties can be classified into 2 categories: physical properties, such as color, odor, melting point, boiling point, density, etc., and chemical properties, like composition, combustibility, reactivity with acids and bases, etc. Physical properties can be measured or observed without changing the identity or the composition of the substance. The measurement or observation of chemical properties requires a chemical change to occur. Measurement of physical properties does not require occurrence of a chemical change. The examples of chemical properties are characteristic reactions of different substances. These include acidity or basicity, combustibility, etc. Chemists describe, interpret and predict the behavior of substances on the basis of knowledge of their physical and chemical properties, which are determined by careful measurement and experimentation. In the following section, we will learn about the measurement of physical properties. 1.3.2. Measurement of physical properties. Quantitative measurement of properties is required for scientific investigation. Many properties of matter, such as length, area, volume, etc., are quantitative in nature. Any quantitative observation or measurement is represented by a number followed by units in which it is measured. For example, length of a room can be represented as 6 meters, here. 6 is the number and m denotes meter, the unit in which the length is measured. Earlier, 2 different systems of measurement, tatis, the English system and the metric system, were being used in different parts of the world. The metric system, which originated in France in late 18th century, was more convenient as it was based on the decimal system. Late, need of a common standard system was felt by the scientific community. Such a system was established in 1960 and is discussed in detail below. 1.3.3. The International System of Units (SI). The International System of Units, in French Le Système International d'Unités, abbreviated as SI, was established by the 11th General Conference on Weights and Measures (CGPM) from Conférence Générale des Poids et Mesures. The CGPM is an intergovernmental treaty organization created by a diplomatic treaty known as Meter Convention, which was signed in Paris in 1875. The SI system has 7 base units and they are listed in Table 1.1. These units pertain to the 7 fundamental scientific quantities. The other physical quantities, such as speed, volume, density, etc., can be derived from these quantities. The definitions of the SI base units are given in Table 1.2. The SI system allows the use of prefixes to indicate the multiples or submultiples of a unit. These prefixes are listed in Table 1.3. Let us now quickly go through some of the quantities which you will be often using in this book. 1.3.4. Mass and weight. Mass of a substance is the amount of matter present in it, while weight is the force exerted by gravity on an object. The mass of a substance is constant, whereas its weight may vary from one place to another due to change in gravity. You should be careful in using these terms. The mass of a substance can be determined accurately in the laboratory by using an analytical balance, figure 1.5. The SI unit of mass as given in Table 1.1 is kilogram. However, its fraction named as gram, 1 kilogram equals 1000 grams, is used in laboratories due to the smaller amounts of chemicals used in chemical reactions. 1.3.5. Volume. Volume is the amount of space occupied by a substance. It has the units of length power 3. So in SI system, volume has units of meter power 3. But again, in chemistry laboratories, smaller volumes are used. Hence, volume is often denoted in cm power 3 or dm power 3 units. A common unit, liter, L, which is not an SI unit, is used for measurement of volume of liquids. 1 liter equals 1000 milliliters, 1000 centimeters power 3 equals 1 decimeter power 3 in the laboratory. The volume of liquids or solutions can be measured by graduated cylinder, burette, pipette, etc. A volumetric flask is used to prepare a known volume of a solution. These measuring devices are shown in Figure 1.7. 1.3.6. Density. The two properties, mass and volume discussed above are related as follows. Density equal to mass per volume. Density of a substance is its amount of mass per unit volume. So, SI units of density can be obtained as follows. SI unit of density equal to SI unit of mass per SI unit of volume kilogram m power 3 or kilogram m power minus 3. This unit is quite large and a chemist often expresses density in gcm power minus 3, where mass is expressed in gram and volume is expressed in cm power 3. Density of a substance tells us about how closely its particles are packed. If density is more, it means particles are more closely packed. 1.3.7. Temperature. There are three common scales to measure temperature: degree Celsius, degree Fahrenheit, and K Kelvin. Here, K is the SI unit. The thermometers based on these scales are shown in figures 1.8. Generally, the thermometer with Celsius scale are calibrated from 0 degrees to 100 degrees, where these two temperatures are the freezing point and the boiling point of water, respectively. The Fahrenheit scale is represented between 32 degrees to 212 degrees. The temperatures on two scales are related to each other by the following relationship: degree Fahrenheit equals 9, divided by 5, degree C, plus 32. The Kelvin scale is related to Celsius scale as follows: K equals degree C plus 273.15. It is interesting to note that temperature below 0 degrees Celsius, that is, negative values, are possible in Celsius scale, but in Kelvin scale, negative temperature is not possible. 1.4. Uncertainty in measurement. Many a time in the study of chemistry, one has to deal with experimental data as well as theoretical calculations. There are meaningful ways to handle the numbers conveniently and present the data realistically with certainty to the extent possible. These ideas are discussed below in detail. 1.4.1 Scientific notation, as chemistry is the study of atoms and molecules, which have extremely low masses and are present in extremely large numbers, a chemist has to deal with numbers as large as 602. 200 quintillion for the molecules of 2 grams of hydrogen gas are as small as 0.00000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000Speed of light, charges on particles, etc., speed of light, charges on particles, etc., involve numbers of the above magnitude. It may look funny for a moment to write or count numbers involving so many zeros, but it offers a real challenge to do simple mathematical operations of addition, subtraction, multiplication or division with such numbers. You can write any two numbers of the above type and try any one of the operations you like to accept as a challenge, and then you will really appreciate the difficulty in handling such numbers. This problem is solved by using scientific notation for such numbers, that is, exponential notation, in which any number can be represented in the form n times 10 power n, where small n is an exponent having positive or negative values and capital N is a number, called digit term, which varies between 1.000 and 9.999. Thus, we can write 232.508 as 2.32508 times 10 power 2 in scientific notation. Note that while writing it, the decimal had to be moved to the left by 2 places, and same is the exponent 2 of 10 in the scientific notation. Similarly, 0.00016 can be written as 1.6 times 10 power minus 4. Here, the decimal has to be moved 4 places to the right, and minus 4 is the exponent in the scientific notation. While performing mathematical operations on numbers expressed in scientific notations, the following points are to be kept in mind. Multiplication and division. These two operations follow the same rules which are there for exponential numbers, that is, 5.6 into 10 power 5 into 6.9 into 10 power 8 equals to 5.6 into 6.9 into 10 power 5 plus 8 equal to 5.6 into 6.9 into 10 power 13 equals to 38.64 into 10 power 13 equals to 3.864 into 10 power 14. 9.8 into 10 power minus 2 into 2.5 into 10 power minus 6 equals to 9.8 into 2.5 into 10 power minus 2 plus minus 6 equals to 9.8 into 2.5 into 10 power minus 2 minus 6 equal to 24.50 into 10 power minus 8 equals to 2.450 into 10 power minus 7. 2.7 into 10 power minus 3 divided by 5.5 into 10 power 4. After solving this, we will get 4.909 into 10 power minus 8. Addition and subtraction. For these two operations, first the numbers are written in such a way that they have the same exponent. After that, the coefficients, digit terms, are added or subtracted as the case may be. Thus, for adding 6.65 times 10 power 4 and 8.95 times 10 power 3, exponent is made same for both the numbers. Thus, we get 6.65 times 10 power 4 plus 0.895 times 10 power 4. Then, these numbers can be added as follows: 6.65 plus 0.895 times 104 equals 7.545 times 10 power 4. Similarly, the subtraction of two numbers can be done as shown below. 2.5 into 10 power minus 2 minus 4.8 into 10 power minus 3 equals to 2.5 into 10 power minus 2 minus 0.48 into 10 power minus 2 equal to 2.5 to 0.48 into 10 power minus 2 equal to 2.02 into 10 power minus 2 1.4.2. Significant figures. Every experimental measurement has some amount of uncertainty associated with it because of limitation of measuring instrument and the skill of the person making the measurement. For example, mass of an object is obtained using a platform balance and it comes out to be 9.4 grams. On measuring the mass of this object on an analytical balance, the mass obtained is 9.4213 grams. The mass obtained by an analytical balance is slightly higher than the mass obtained by using a platform balance. Therefore, digit 4 placed after decimal in the measurement by platform balance is uncertain. The uncertainty in the experimental or the calculated values is indicated by mentioning the number of significant figures. Significant figures are meaningful digits which are known with certainty plus one which is estimated or uncertain. The uncertainty is indicated by writing the certain digits and the last uncertain digit. Thus, if we write a result as 11.2 milliliters, we say the 11 is certain and 2 is uncertain, and the uncertainty would be plus or minus 1 in the last digit, unless otherwise stated. An uncertainty of plus or minus 1 in the last digit is always understood. There are certain rules for determining the number of significant figures. These are stated below. 1. All non-zero digits are significant. For example, in 285 centimeters, there are 3 significant figures, and in 0.25 milliliters, there are 2 significant figures. 2 zeros preceding to first non-zero digit are not significant. Such zero indicates the position of decimal point. Thus, 0.003 has one significant figure and 0.0052 has two significant figures. 3 zeros between two non-zero digits are significant. Thus, 2.005 has four significant figures. 4 zeros at the end or right of a number are significant, provided they are on the right side of the decimal point. For example, 0.200 grams has 3 significant figures. But, if otherwise, the terminal zeros are not significant if there is no decimal point. For example, 100 has only one significant figure, but 100 has 3 significant figures and 100.0 has 4 significant figures. Such numbers are better represented in scientific notation. We can express the number 100 as 1 times 10 power 2 for one significant figure, 1.0 times 10 power 2 significant figures, and 1.00 times 10 power 2 for 3 significant figure. 5. Counting the numbers of object. For example, 2 balls are 20x, have infinite significant figures as these are exact numbers and can be represented by writing infinite number of zeros after placing a decimal, that is, 2 equals 2.000000 or 20 equals 20.000000. In numbers written in scientific notation, all digits are significant. Example, 4.01 times 10 power 2 has 3 significant figures, and 8.256 times 10 power minus 3 has 4 significant figures. However, one would always like the results to be precise and accurate. Precision and accuracy are often referred to while we talk about the measurement. Precision refers to the closeness of various measurements for the same quantity. However, accuracy is the agreement of a particular value to the true value of the result. For example, if the true value for a result is 2.00 grams and student A takes two measurements and reports the results as 1.95 grams and 1.93 grams. These values are precise as they are close to each other but are not accurate. Another student, B, repeats the experiment and obtains 1.94 grams and 2.05 grams as the results for two measurements. These observations are neither precise nor accurate. When the third student, C, repeats these measurements and reports 2.01 grams and 1.99 grams as the result, these values are both precise and accurate. This can be more clearly understood from the data given in Table 1.4. Addition and subtraction of significant figures. The result cannot have more digits to the right of the decimal point than either of the original numbers. 12.11, 18.01, 0.012, 31.122. Here, 18.0 has only one digit after the decimal point and the result should be reported only up to one digit after the decimal point, which is 31.1. Multiplication and division of significant figures. In these operations, the result must be reported with no more significant figures as in the measurement with the few significant figures. 2.5 times 1.25 equals 3.125 since 2.5 has two significant figures. The result should not have more than two significant figures, thus, it is 3.1. While limiting the result to the required number of significant figures as done in the above mathematical operation, one has to keep in mind the following points for rounding off the numbers. 1. If the rightmost digit to be removed is more than 5, the preceding number is increased by 1. For example, 1.386. If we have to remove 6, we have to round it to 1.39. 2. If the rightmost digit to be removed is less than 5, the preceding number is not changed. For example, 4.334. If 4 is to be removed, then the result is rounded up to 4.33. 3. If the rightmost digit to be removed is 5, then the preceding number is not changed if it is an even number but it is increased by 1 if it is an odd number. For example, if 6.35 is to be rounded by removing 5, we have to increase 3 to 4 giving 6.4 as the result. However, if 6.25 is to be rounded off, it is rounded off to 6.2. 1.4.3. Dimensional analysis. Often while calculating, there is a need to convert units from one system to the other. The method used to accomplish this is called factor label method or unit factor method or dimensional analysis. This is illustrated below. Example, a piece of metal is 3 inch, represented by in, long. Solve problems U. 1. A piece of metal is 3 inch, represented by in, long. What is its length in cm? 2. A jug contains 2 liters of milk. Calculate the volume of the milk in meter power 33. How many seconds are there in 2 days?